8th International Physics Olympiad, year 1975, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Measure me if interested. My email is fred1996@hotmail.com or use Skype name Eduard F1996. Problem number 1. Rotating rod. A rod revolves with the constant angular velocity omega around the vertical axis A. The rod includes a fixed angle of pi over 2 minus alpha with the axis. A body of mass m can glide along the rod. The coefficient of friction is null, equal tangent beta. The angle beta is called friction angle. Question A. Determine the angles alpha under which the body remains at rest and under which the body is in motion if the rod is not rotating. It means omega equals 0. Question B. The rod rotates with a constant angular velocity omega greater than 0. The angle alpha does not change during rotation. Find the condition for the body to remain at rest relative to the rod. You can use the following relations. Solution for problem number 1. Let's check the first case A, when omega equals 0. In that case we have two equations for free body diagram. We suppose that our body is not moving. In that case, in a direction parallel to the slope, we have mg sine alpha equal force of friction, and perpendicular to the slope, mg cosine alpha equal normal force. In our case, force of friction must be less or equal to mu n. So it means that force of friction must be less or equal to mu mg cosine alpha, and we can combine these two equations to find this one, and finally that tangent alpha must be less or equal to mu, which is tangent of a critical angle beta. So for that case, this body is not moving. If tangent alpha greater than mu equal tangent beta, our body will move down, and this is the solution for question A. Solution for case B, when omega greater than 0. First, we suppose that this omega, or beta r omega square, very small. In that case, force of friction still going to the up and the right, and we can write the expressions for both forces like this. Now in our rotational frame of reference we have additional force mr omega square, which is going out of the center of rotation, and both equations have these expressions. Again, for critical force of friction F equal mu n. In that case we have these two equations, and now we can put expression for n here and use mu equal tangent beta. So we have this one. Now we can multiply everything by cosine beta, and we will get this formula. Now we can see that here we have sine alpha minus beta, and here we have cosine alpha minus beta. So we have this one. In case of critical angle we have this one. We can see that for small r and omega square, still for alpha less than beta, our body is not moving, but we can make angle alpha greater than beta, and for some relation between r omega square over g, we can exceed tangent alpha minus beta, this number. In that case, our body will go down. In this tangent less than this expression, it will not go anywhere. So that was a solution for small r omega square. Now let's check what happened in case B when r omega square big enough that force of friction F must go downhill to compensate ability for body to go up and right. So in that case we can rewrite our equations in form of this one, where force of friction F changed the sign. Now imagine that force of friction F has critical expression mu n. In that case we have this expression, and now we can put this n to the first formula, and instead of mu again we can use tangent beta. So we have this expression. Now again we can multiply both parts by cosine beta, and we will get this one. And in this case we have for both parts expressions for function alpha plus beta. So we have this one and finally this one. Because this is the expression for critical angle, it means that if tangent alpha plus beta exceeds this expression, our body is not moving anywhere. But if this tangent became less than this expression, the body starts to move up and right. So that was a full solution for problem number 1. 8th International Physics Olympiad year 1975 IPHO. I offer private tutoring for physics Olympiad preparation. I currently have openings. Measure me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F1996. Problem number 2. The focal length f of a thick glass lens in air with a refractive index n, radius curvatures r1 and the r2, and the vertices distance d, see the figure, is given by formula f equal this expression. Remark: Ri greater than 0 means that the central curvature point Mi is on the right side of the aerial vertices Si. Ri less than 0 means that the central curvature point Mi is on the left side of the aerial vertices Si, where I equal 1 or 2. For some specific applications, it is required that the focal length is independent from wavelength. Question A. For how many different wavelengths can the same focal length be achieved? Question B. Describe a relation between Ri, where I equal 1 or 2, d, and the refractive index n, for which the required wavelength independence can be fulfilled, and discuss this relation. Sketch possible shapes of lenses and mark the central curvature points M1 and M2. Question C. Prove that for a given plane convex lens, a specific focal length can be achieved by only one wavelength. Question D. State possible parameters of the thick lens For two further cases in which central focal length can be released for one wavelength only, take into account the physical and the geometrical circumstances. Solution for problem number 2. Question A. For how many different wavelengths can the same focal length be achieved? Solution. The refractive index n is a function of the wavelength lambda. According to the given formula for the focal length f, which for a given f yields to a quadratic equation, in n there are at most two different wavelengths indices of refraction for the same focal length. So that was a solution for question A. Solution for question B. Describe a relation between Ri, I equal 1 or 2, D and the refractive index n, for which the required wavelength independence can be fulfilled, and discuss this relation. Solution. If the focal length is the same for two different wavelengths, then we have equation f from n1 equal f from n2. Using the given equation for the focal length, it follows from equation we have this equation for both coefficients of refraction. Now we can reverse them and find that we have this relation. Now we can simplify it to this equation, and after subtraction we have this relation. If n1 not equal n2, which is obvious, we can get finally this relation. R1 minus R2 equal D multiplied by 1 minus 1 over N1 and 2. If the values of the radii R1, R2 and the thickness satisfy this condition, the focal length will be the same for two wavelengths indices of refraction. The parameters in this equation are subject to some physical restrictions. The indices of refraction are greater than 1, and the thickness of the lens is greater than 0. Therefore, equation 2 became D greater than R1 minus R2 and R1 greater than R2. So that was solution for question B. Question C. Prove that for a given plane convex lens, a specific focal length can be achieved by only one wavelength. If we take this formula for focal length and suppose that R2 is going to infinity, we can get limit f going to R1 over n minus 1, which is formula for regular thin lens. And this thin lens has only one root. That was solution for question C. Question D. State possible parameters of the thick lens for two further cases in which a certain focal length can be released for one wavelength only. Take into account the physical and the geometrical circumstances. Solution for question D. Again, we can use equation for focal length. It should have only one single root, and we can rewrite it in form of regular quadratic triplet. So that will be this equation. Here we can use regular substitutions for coefficients A, B and C. That will be this one. And from here we can write solution for two roots of this equation. That will be this one. But we have to use cases when we have only one root. That could happen in three different cases. So first case is when this triplet became duplet. it means that A equals 0, and this equation became linear equation. So we have A equals 0, it means that R1 minus R2 equals G, and in that case coefficient of refraction n equals this expression, which must be greater than 1. So that was first case. Second case, it happened when coefficient b equals 0. It means that we have two roots, one is positive and the other is negative, and because negative doesn't make us physical sense, we have only one positive root. So that will be b equals 0, this expression equals 0, and because n squared equals negative c over a, which is equal to this expression, the root will be positive quadratic root from this expression, which must be greater than 1. So that was second solution. And the third solution is when this discriminant equals 0. So that will be b squared minus 4ac equals 0. And we have this expression. In that case, we have two roots, but they are equal to each other, and they are equal to negative b over 2a, which is this expression, and this expression also must be greater than 1. So we did all 4 questions for problem number 2. 8th International Physics Olympiad, year 1975, IPHO. I offer private tutoring for physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F. 1996. Problem number 3. Ions in a magnetic field. A beam of positive ions, charge positive E, of the same and constant mass m, spread from point Q in different directions in the plane of paper. See figure. The ions were accelerated by a voltage U. They are deflected in a uniform magnetic field B that is perpendicular to the plane of paper. The boundaries of the magnetic field are made in a way that the initially diverging ions are focused in point A, QA equal to A. The trajectories of the ions are symmetric to the middle perpendicular on QA. Among different possible boundaries of magnetic fields, a specific type shall be considered in which a continuous magnetic field acts around the middle perpendicular and in which the point Q and A are in the field-free area. Question A. Describe the radius curvature R of the particular path in the magnetic field as a function of the voltage U and the induction B. Question B. Describe the characteristic properties of the particle paths in the setup mentioned above. Question C. Obtain the boundaries of the magnetic field, boundaries by geometrical constructions for the cases R less than A, R equal A, and R greater than A. Question D. Describe the general equation for the boundaries of the magnetic field. Solution for problem number 3. Question A. Describe the radius curvature R of the particle path in the magnetic field as a function of the voltage U and the induction B. Solution. The kinetic energy of the ion after acceleration by voltage u is this one, 1/2 mv square equal EU. From this equation, the velocity of the ions is calculated by v equal square root from 2 EU over m. On a moving ion, charge E and velocity v in a homogeneous magnetic field B acts a Lorentz force F. Under the given condition, the velocity is always perpendicular to the magnetic field. Therefore, the paths of the ions are circular with radius r. Lorentz force and the centrifugal force are of the same amount. So we have EVB equal mv square over r. And from this equation, the radius of the ion path is calculated. R equal 1 over b multiplied by square root from 2mu over e. That was a solution for question A. Question B. Describe the characteristic properties of the particle path in the setup mentioned above. Solution. And ions of mass m travel on circular paths of radius r equal this expression Vm over Eb inside the magnetic field. Leaving the magnetic field, they fly in a straight line along the last tangent. The centers of curvature of the ion paths lie on the middle perpendicular of QA, since the magnetic field is assumed to be symmetric to the middle perpendicular on QA. The paths of the focused ions are above QA due to the direction of the magnetic field. So that was a solution for question B. Question C. Obtain the boundaries of the magnetic field. Boundaries by geometrical constructions for the cases r less than a, r equal a, and r greater than a. Solution. The construction method of the boundaries of the magnetic fields is based on the considerations in part B. Circles of radius r and different centers of curvature on the middle perpendicular QA. Sketch tangents on the circle which either point Q or point A on these straight lines. The points of tangency make up the boundaries of the magnetic field. If R greater than A, then no tall ions will reach point A. Ions starting at the angle taper than the tangent at Q do not arrive in A. The figure on this page shows the boundaries for the magnetic fields for the three cases R less than A, R equal A, and R greater than A. Question D. Describe the general equation for the boundaries of the magnetic field. Solution. It is convenient to reduce a general equation for the boundaries of the magnetic field in polar coordinates r and phi, instead of using Cartesian coordinates x, y. The following relation is obtained from the figure. From this figure we have small r multiplied by cosine phi plus r sine phi equal a. The boundaries of the magnetic field are given in that case by equation small r equal a over cosine phi multiplied by 1 minus big R over a sine phi. That was a solution for question D, and here we solve all questions for problem 3.